Hey, welcome. Have you ever seen one of these things at a junkyard before? They're pretty amazing. These electromagnets, what they do is they drive a bunch of current through here and that becomes magnetized. Then they can pick up metal pieces, move them around the junkyard where they need to be, and then stop the current through here, which stops the magnetic fields. And that turns the magnetism off. It's pretty amazing. And it's a good visual device to understand what's going on when you talk about electromagnetism because it's the current, the electric current that causes something to become magnetized when you have an electromagnet, which is pretty amazing technology. In fact, almost all of our modern society depends on electric motors and electric generators. So that's where we're going with this. We're going to take one more important step today in understanding how to get there. So maybe you're a physics student and you need to know something about electromagnetism or solenoids and electromagnets and the right-hand rule for a current with a wire. That's what we're going to be talking about today. So one very, very important property of electromagnetism is the idea that an electrical current causes a nearby magnetic field. And on the flip side of that, a moving magnetic field causes a current in a nearby conductor. So this first sentence right here is what allows all electromagnets and all electric motors to work. And we're going to get to that eventually. It'll take us a few lessons to be able to get there. And this second sentence over here is the basis for all generation of electricity that we need to make our modern society run. So let's go ahead and learn a little bit more about this. So first of all, I do want to say that there is a right-hand rule here that you're going to need to learn, and it's easiest if you just have a pencil or a pen and you point the thumb of your right hand in the direction of the conventional currents, and the curl of your fingers will show the direction of the magnetic field that's created by that moving current. Fundamentally, we're talking about a three-dimensional structure on a two-dimensional surface, the screen in front of you, so that's why we need to use analogies to better understand what's happening here. And if you see a point, that is going to represent a current that's coming towards you. Think about the point of an arrow, and the backside of an arrow will be a cross, and we'll get to that in a moment. If you imagine the backside of an arrow having feathers and the backside in the shape of an X, that's what we mean. I'll show you that in a moment. But if you imagine your pencil coming straight at you and you point your thumb towards you and the curl of your fingers of your right hand would be in this direction right here. So from this viewpoint, it would be counterclockwise. All right, well, let's take a look at another way of thinking about this from a slightly different angle. If the current was coming out in 3 dimensions in this plane right here, same kind of thing. Imagine your thumb pointing in the direction of this conventional current right here, and the curl of your fingers of your right hand will show the direction of the magnetic fields that's created because of that moving charge, because of the charge that's moving on the surface of the conductor, which is what we call current. All right, and so I wrote it out right here. It says when the thumb of the right hand points in the direction of the conventional current, then the curl of the finger shows the direction of the magnetic field produced. So let's go ahead and see if you can answer some practice questions and think through this. So I wrote, use your pen or your pencil and your right hand and draw the current and then the magnetic field for each of the 6 examples below. So let me do the first one. I think you'll understand more once I do the first one for you. Imagine your right hand is going to be pointing to the right, and the curl of your fingers will be around the pencil, or you could say the curl of your fingers will show the direction of the magnetic fields that's created by that moving current. And if something's coming towards you, we're going to draw it as a dot, and if it's going away from you, we're going to draw it as an X. We have to do something similar because we're dealing with a 3-dimensional phenomenon in 2 dimensions. So let me show you what it looks like. Above the wire, so this represents the wire right here, above the wire, you're going to have magnetic field that's coming towards you, and below the wire, you're going to have magnetic field moving away from you. The magnetic field is represented by a B and current is represented by I. Now I want you to think to yourself, all right, what would we do for this? For example, B. And you will learn more if you actually do this. If you take your right hand, point it to the left, and think about the curl of your fingers, and in the curl of your fingers would represent the wire. So above the wire, what is the magnetic field doing? And below the wire, what is the magnetic field doing? Well, hopefully you're able to come up with something like this. Above the wire, the magnetic field is going into the screen or away from you, and below the wire, the magnetic field is going to be coming out towards you. All right, well, what about C over here? What do you think? What does this represent? Well, remember, if you're looking at a dot, that means it's coming towards you. So imagine your thumb of your right hand is going to be pointing towards you. What would be the direction of the magnetic field that's created created by that current? Well, the direction is going to be like this, right? It's going to be counterclockwise. Well, what about this example? What does this example, first of all, mean? Well, it means that the current is going to be going into the page. So if you imagine your thumb of your right hand pointing into the screen right now, the curl of the fingers of your right hand will show the direction of the magnetic field that's created. So it's going to look like this. It's going to be a clockwise magnetic field that's created from this point of view, we could say. How about E? Take a look at E. What do you think? What's the direction of the magnetic field going to be? Well, pointing the thumb of your right hand downwards, you can see that the curl of your fingers of your right hand are going to go into the page over here and out of the page over here. Lastly, on this side, we have current going upwards, the magnetic field going out of the page here into the page over here. And if you can understand that now, you get one of the main ideas that we're going to be going over today, and that is how to recognize the direction of the magnetic field that's created by a current. By the way, when I say conventional currents, that just means like the standard currents. And I've talked about this previously. I can put a link up to a screencast I've done on currents, but the idea is that positive charges are flowing in the direction of the currents. That's actually not true. It's really electrons, which are negative charge carriers, that are going to be the particles that carry the charge that actually flow across the surface of a conductor in most cases, if you're talking about like a metal wire, for instance. All right. In any case, let's continue and see what else there is to know. All right, this is just another visualization. If you think about the magnetic field that's created by a current flowing through a wire, I want you to think about why this is. And to do that, take your right hands and point it in the direction of these red arrows, which show the direction of the current, and that will help you to visualize the direction of the magnetic field that's created by that moving current. All right, and real quick, we need to talk briefly about something called magnetic domains. I've done another screencast that includes information about this as well, but just to quickly summarize, we're going to say magnetic domains. These are small areas inside materials that can be magnetized that essentially have an unbalanced number of electrons that are not paired up in their electron configuration. You can almost think of it as having a lopsided spin of electrons, and what that does is it creates a tiny magnetic field. These magnetic fields all kind of work together in a small area called a domain. And when the domains start to line up more and more, you get more and more adding up of these small little magnetic field vectors that all add up to something much greater. This might be a small magnetic field. The net field is going to be up slightly. Over here, it's even more of a net field going up slightly. So this is going to be a medium strength magnet. Over here, this is a stronger magnet because all of its domains are pointing in the same direction. And it turns out that if you put something like iron that's ferromagnetic into a strong magnetic field, it can line itself up and it can add to the effect. And that's an important concept that we're going to use right about now. All right, so I want you to think about a wire that's been turned into a coil section. And as the current flows through this wire, what it's going to do is produce a magnetic field. And so now in this case, these dots right here don't represent magnetic field coming out at you. These represent currents coming out at you. And these down here represent current going away from you in the same sense that the current down here is going away from you. Down here is going away from you. And up top is coming towards you, coming towards you. And that's what we're showing right here. As a result, you get a magnetic field. And it makes sense to say, well, if my thumb was pointing towards me right here, the curl of my fingers of my right hand would have a clockwise direction right here. So these lines that you see right here are the magnetic field that's created from something like this. Well, check it out. They all kind of build on top of each other. And in fact, this looks very, very similar to the magnetic field of a magnet. So if you have a coil of wire with a strong enough current and enough turns of that coil of wire, you can make it act like a magnet, because this magnetic field will build on itself and it will start to act just like a magnet. So if you think back to the junkyard electromagnet that's able to pick up pieces of metal with iron in it, that's what we're talking about here, because as long as you have current flowing through this, it can act like a magnet. All right, so I can show you over here. This is the magnetic fields of a bar magnet right here. This is what's called a solenoid. If you have a coil of wire that's set up in such a way that it has a decent amount of current flowing through it and it acts like a magnet right here. Well, something else happens. This solenoid right here will get even stronger if you can put an iron core in here, because if you can put an iron core in here and actually wrap the solenoid around the iron core, you've created what truly is an electromagnet. It's pretty amazing. That makes a solenoid stronger. It makes an electromagnet is like a solenoid, but better. And that's because these magnetic domains in here now line up. They reinforce what's happening. The domains are all pointing in the same direction for the iron core right here. And so it reinforces itself. It has a greater effect if you have an electromagnet as opposed to a solenoid. But for now, I think you can start to understand how an electric current can turn something like an iron core into an electromagnet, which is pretty amazing stuff. And again, you see a solenoid over here. It's got the magnetic field that we had talked about. And basically, that's more or less the same magnetic field that you would see in a magnet and the same field that you would see in an electromagnet. It's just that the electromagnet would be self-reinforcing, so it would be even greater in terms of the magnetic force that's produced. And that's how you're able to pick stuff up. And so hopefully now you can understand a little bit about how an electromagnet can pick up iron pieces. And that's it. Hopefully this has been helpful. If you have any comments down below, please let me know. And I hope you all have a great day. Take care.